a little bit about lesson 1, oxidation and reduction. So oxidation and reduction. Many chemical reactions, of course, involve the transfer of electrons from one substance to another. We looked at sodium chloride as an example. So let's go to sodium chloride here. I said if you were going to draw some sodium chloride, I said you would take sodium, which looks like this, chlorine, and you would show me electrons moving over. And if you mix those two things together, you get sodium with a 1 plus and chlorine with a 1 minus. Yes? Okay. So it is the transfer of electrons, of course. Something is gaining electrons, something is losing electrons. In this case here, sodium, of course, is losing electrons to, well, losing an electron to chlorine. Chlorine's gaining that electron, yes? Okay. So then we talked about oxidation and reduction. These are very important terms for you guys for this unit. Oxidation, of course, is the loss of an electron. So if we go back to our example here, which one is being oxidized? Sodium is being oxidized, yes? It is losing the electron. And then we talked a little bit about reduction. And reduction, of course, is the gaining of electrons. In this case, chlorine is gaining electrons, so it is being reduced, yes? And you can think about that in terms, of course, as charges as well. If you look at sodium here, okay, so this is the oxidation half reaction. If you look at sodium, sodium becomes a sodium 1 plus and 1 electron. Okay? So it is losing electrons, sodium is being oxidized. It's going from a 0 charge to a 1 plus charge. So it's being oxidized. And then the easier one to actually do is reduction. Okay? So if you think about which one is being reduced here, it's chlorine. And you would say Cl, well, technically Cl, we're going to do this later here, but Cl2, okay, becomes chloride, by gaining 2 electrons. Okay, that would be the half reaction for chlorine. Okay, and once again, that looks a little complicated, perhaps, but we'll talk about that in a little bit here. That is the one that's being reduced. Look, it's going from a 0 charge to a 1 minus. It is going down in numbers, 0 to a 1 minus, so it is being reduced. Okay, and that is the reduction. Okay, and there's some examples there for you as well. Do you guys have all these notes or no? Okay, do you guys have the one from before here? Do you have this one? Oh, sorry. Okay, I'll pause it here and you guys can copy. I thought we were a little farther here, but reduction is the gain of electrons by a substance during chemical reaction. Chemicals that are typically reduced include metal ions and non-metal atoms. If you think about the non-metals, they want to gain electrons to fill out their outside energy level, right? So, in a reduction half reaction, the gained electrons are shown as the reactant. Okay, and here's a few examples for you here as well. I'll just pause it for you. Okay, so oxidation, of course, electrons are lost. Remember, just a little bit of review here. When we write electrons lost, we did this last day, I believe, but you know, we don't write minus electrons. We always add them, right? So we don't see this, for example, copper in this case here, minus 2 electrons gives me copper 2 plus. We wouldn't write that because we never use minuses in a chemical equation, right? So how are we going to represent lost electrons? Well, we write them on the product side. So copper loses 2 electrons. Those are the 2 electrons that have been lost, and you get the copper 2 plus ion. What you also know is this is called the oxidation half reactions, of course. What you also know is that both sides of these equations add up. What's the charge on this copper right here? It's 0. There's no charge on it. And this is a 2 plus, and this is a 2 minus, 2 negative electrons. 0 versus 0. Okay? That's good. That's what we want. Okay? So that's oxidation. Reduction is gaining of electrons, so we write them on the reactant side. Okay, they're gaining electrons, they're bringing electrons in. So Ag plus and 1 electron gives you Ag solid, for example. So we have oxidation, which loses electrons. We have reduction, which takes in those electrons. And of course, those two happen simultaneously. They happen at the same time. If you want to remember which one's which, look, reactant side is the reduction. They both start with Re, right? So if you're not sure where to put electrons or which type of equation you have, the reduction always has electrons on the reactant side, Re, Re, okay? Reduction's reactant, okay? Electrons. So you'll see reduction, of course, on the reactant side, and this is also, and this is also on the reactant side. So it's a reduction, okay? And like I said, those two take place at the same time. Reduction and oxidation must take place at the same time. The overall reaction is known as the redox reaction. Or I like to call it Redox reaction. Redox. Oxes aren't red, silly. They're brown or something. White, maybe. Oxes aren't yellow. That's a yak, exactly. As in, I sure like chemistry because it's not yucky. Anyway, the point here is that's a redox reaction when you write those two half reactions together, okay? Yeah. Those two have to happen at the same time. The overall equation, which we're going to do today, is the redox reaction. This looks confusing because it is, because these didn't match up here, so just be patient here for a second. If you take a look at the reaction between zinc and copper 2 sulfate, you can write this down here, guys. I'm going to take some of this stuff out here. Don't worry about the gains 2 electrons and loses 2 for right now. Just copy those 3. Okay, so reaction between zinc and copper 2 sulfate, and these would be the 3 reactions that are kind of we could write out on these. Do you remember what these are called? We did these in Chem 20. What's this one called up here? Single replacement. When in Chem 20 you would have called this the what is that? Remember? The oh, come on. Molecular equation. This one here would be called the ionic equation. Yes? And this one here would have been called the net ionic equation. Molecular, ionic, net ionic. Yes, true. Now, mini. Yeah, meep. Does that sound familiar? Because I use that joke every year. Molecular, ionic, net ionic. Meep, mini. Here I come in my Mini Cooper. Okay. So look. Okay. What's the charge? By the way, what's the charge on this zinc right here? No charge. That's right. Because it's by itself, right? Yes? So you don't get charges if it's by itself. What's the charge on this copper here? 2 plus. Right? Sulfate, 2 minus, yes? Okay, pay attention. Copper, 0 here, right, by itself. 2 plus, 2 minus, yes? So those are the charges that kind of go with that stuff, yes? Correct? Okay, so we would write out here's the ionic equation, etc., etc. Look what happens. Zinc goes from zinc 0 to zinc 2 plus. How does that happen? How does zinc become zinc 2 plus? It loses 2 electrons. So you're going to write that in here. Loses 2 electrons, yes? Therefore, is that being reduced or oxidized? Oxidized, okay? Look at copper 2 plus here. Goes to copper. Okay? 2 plus, copper 2 plus goes to copper 0. How does that happen? Gains 2 electrons, yes? Copper 2 plus gains 2 electrons, yes? So that one is, of course, being reduced, correct? correct? Okay. 2 plus to 0. 2 plus, think about a number line, guys. You know, I like to think of it in this way, but you can do it this way too. But if you think of a number line, 2 plus is here, it's going down to 0. It's being reduced. It's going down in charge, right? 2 plus to 0. Oxidized means it's going up in charges. So if you think about oxidized here, which one did we say? 0. Now it's going up to a 2 plus. So 0 to 2 plus, that's being oxidized if you're going up in charges. Okay? So that's what happens in a single replacement reaction. By the way, if you remember about mini reactions, what about the sulfate? What's that deal there? Sulfate goes from a 2 minus to what? A 2 minus? Yes? What's that called? Nope. What's these two things? What is that called in this case? Mini reactions. Oh, come on, guys. We did this in Unit 4. It is a, starts with a S. No. Spectator ion. Okay? So this is your spectator ion, and obviously the same on both sides, right? Doesn't change in charge, doesn't gain or lose electrons. Same on both sides. That's your spectator ion. That's Chem 20. Spectator ion. Remember, what's its job? Well, its job is to get charges on, for example, in this case, it's the job to get the copper 2 plus. Because remember, if it was just copper by itself doesn't have a charge, and neither does zinc by itself. But if you get the ionic compound copper 2 plus, those 2 electrons had to go somewhere. That's how I get the sulfate. Okay? Those 2 electrons that were lost there were gained by the sulfate initially. But what we have later on here in the single replacement is a transfer of electrons from one metal to another metal. Okay? All right. So moving on here. Now, this is a very important key term here, and so is the next one. So we're going to talk about oxidizing agents. I'll let you guys copy, and we'll talk about this in a seckie here. All right, oxidizing agent, very important. Okay, a chemical which causes the oxidation of another chemical. So the OAs have the ability to take electrons away from another chemical. During the reaction, the oxidizing agent, the OA itself, is being reduced. Okay, OAs take or have the ability to take electrons from another chemical. So let's go back to look at a few of these. I'll come back to that slide in a second here. Let's even go back all the way to this one right here. Right here. Okay? Which one is the OA in sodium chloride? Which one is the OA in sodium and chlorine here? When you mix sodium and chlorine together, OAs are technically, the oxidizing agent is the one that's being reduced. Yes? So you have to remember that. In this case, of course, it's the chlorine being reduced. That is your oxidizing agent. It causes the loss of electrons for sodium. It causes sodium to lose electrons. Okay? That is the OA. If we have an oxidizing agent, okay, so it is the one that's actually being reduced. We also have, of course, the reducing agent, also equally important. Okay? So you guys can copy that one down there. Once again, the reducing agent is a chemical which causes the reduction of another chemical. RAs have the ability to give electrons to another substance, of course, because during the process, the RA itself is being oxidized. So if you think back to this first example, sodium is the one that's being oxidized. Sodium goes from a 0 to a 1 plus. It's being oxidized. So sodium, because it's being oxidized, is the reducing agent. Okay, has the ability to give electrons. All right, good. Are we all done that? Yes, no? Okay, so once again, during the process, the RA itself is going to be oxidized. That's very important that you keep that straight, because we are going to do that over and over and over again. Okay, during a redox reaction, the OA takes electrons from the RA, All right. So, good. Simple redox reactions include formation, decomp, and single replacement. Basically, we looked at a couple of those so far here, but we're going to write these out again. Simple redox reactions include formation, decomp, and single replacement of ionic compounds. Okay. So, let's take a look at the formation of magnesium oxide. So I want you to guys write that down, first of all. Formation of magnesium oxide. Then I want you guys to come up with the equation. I don't need you to balance it, just the equation for the formation of magnesium oxide. If you want to make magnesium oxide, how do you form magnesium oxide? Hopefully this is not too bad for you. So, if I want to make magnesium oxide, by the way, is an ionic compound, of course, is a solid. Ionic compounds tend to be very strong. Yes, they hold together very well due to ionic bonds opposite attract. Magnesium oxide, to make that, you need magnesium and some oxygen is what you should have for that. Yes? That's how you make magnesium oxide. Start out with some two neutral things, right? Magnesium, I kind of ruined it. Magnesium and oxygen, and you combine them together to give you magnesium oxide. You don't need to balance this because we're going to do that right away here. Now you can. I'm just going to tell you right now though, with these I probably actually wouldn't, just because they're on diploma type questions, unit test questions, they're going to ask you for what's the reduction half reaction, what's the oxidation half reaction, et cetera, et cetera. And you may be doing a little extra work if you're going to balance that. It's not a big deal. You can. There's nothing wrong with that. But ultimately, we just kind of want to focus on what's the general, basically, things that are going on here. Now, let me ask you this. So that's kind of my target equation. That's kind of what I'm looking at here. I take magnesium and mix it with oxygen to give me magnesium oxide. What's the charge on this magnesium right here? Nope. Huh? 0. What's the charge on this oxygen? 0. Those two elements combined together, okay, what's the charge on this magnesium? 2 plus. What's the charge on this oxygen? 2 minus. Why do I use charges there? Because it's part of an ionic compound. Ionic compounds have ions. Ions are atoms with charges, right? But you're walking down the street, guys, and you see a chunk of magnesium. You're like, hey, magnesium. There's no charge on that magnesium. Because how do you get charges? You have to gain and lose electrons. What's magnesium losing electrons to if you just see a chunk of magnesium? The answer is nothing. Okay? When you look in the air here, look, there's oxygen right here. There's 2 of them connected together. Why, by the way, why is there 2 of them connected together? Who remembers? What's that called, first of all? Oxygen is a molecular element. Why are they linked together as O2? Why do they come in 2s? Unit 1 from Chem 20. Because they're more stable that way, are they not? They're sharing electrons to fill the outside energy level, yes? 6 valence electrons, double bond in between them, connected together, sharing 8 electrons, octet rule, yes? Okay, so you're walking down the street and you're like, hey, there's oxygen. Now when you take magnesium and you put it with the oxygen, you get them close enough together, and you give them the right conditions, okay? Now magnesium says, hey, I got 2 valence electrons, I'd like to get rid of those. And oxygen's like, hey, I could use those 2, I'll take those, okay? And that's how you get the transfer of electrons. So when you look at this here, we're going to start out with this one here. Magnesium, solid, goes to magnesium 2 plus. And I'm going to put a solid there because I know it's a little bit goofy, but I will put a solid because that's what it forms up there technically. Now, if I'm going from magnesium to magnesium 2 plus, how do I write that as a half reaction? How does magnesium become magnesium 2 plus? Gain or lose electrons? Lose, yes? How many electrons? 2, right? Magnesium to magnesium 2 plus, well, I lose 2 electrons. How do I write losing electrons? I put them over here, right? I add 2 to that side there, correct? If I'm adding 2 to that side, is this an oxidation half reaction or a reduction half reaction? And you should also know by the fact that I'm losing electrons. What is that? Oxidation or reduction? Oxidation. So you're going to put an ox out here. Okay? Good so far? Questions? Yes, no? Okay. Look, left side versus right side. What's the charge here? 0, yes? 2 plus, 2 minus, 0. Does the left side equal the right side? Yes, that's what we want. 1 magnesium, 1 magnesium. Everything's nicely balanced. Okay? Let's look at the next one. O2 becomes O2 minus, right? Yes? Now, before we go any further here, I have 2 oxygens on this side. How many oxygens do I have on the right side? 2? No, only 1, right? This O2, I have 2 here, 2 oxygen atoms. Here I have 1 oxygen atom with gained 2 electrons. So the first thing you're going to have to do is balance it, okay, by putting a 2 out in front. Now I have 2 oxygen atoms on the left side, and I have 2 oxygen atoms with a 2 minus charge on the right-hand side. Okay? So that's the first thing you need to do. Secondly, you need to balance. How did that happen? Well, O2 has gained or lost electrons. Has to be gained because the other one lost, yes? So this one had to gain how many electrons though? Well, for each oxygen, I gain 2 electrons, right? Look up here. This oxygen goes to a 2 minus, right? Each oxygen I gain 2 electrons. I have 2 oxygens, so that's a total of 4 electrons. If you're a little bit confused about that, well, think about it this way. Look, how am I going to balance these 2 sides out? 0 and 4 minus equals 2 minuses, 4 minus, right? Left side has to equal the right side. And once again, if this therefore is my reduction, okay? I know it's my reduction. If you know nothing else, you can say, I know it's reduction because I'm adding electrons to the reactant side. Reactant side electrons equals reduction, R-E-R-E, reduction reactant, okay? You are now going to add these 2 up because these have to happen simultaneously. And when you add these 2 up, you will get what's called the reduction oxidation, or known as the redox reaction. And the redox reaction is the simple adding of these 2 up. But remember, the electrons that I lose has to equal electrons that I gained. That's not the case so far, because I'm losing 2, but I'm gaining 4. That doesn't add up, doesn't match up. So you're going to take this one here, and you're going to multiply it by 2. Okay? Because I need to lose 4 electrons. That means I must have 2 of those oxidation half reactions taking place for every one of the redox ones to match up. Okay? Writing down the final product here, what you have is 2 times magnesium solid, 1 O2. Notice how I lined up all the arrows here, nice and neat. Okay? Gives you, right-hand side, 2 magnesium 2 pluses and 2 O2 minuses. I don't write the electrons down because the electrons that I lost equal electrons I gained, right? We don't write those down in the redox reaction. We don't need to, because you're going to have 4 electrons on the left side, 4 electrons on the right side. Basically, you're going to cancel, right? So, all right. This is the balanced redox reaction that you would have, okay? And this is what's really taking place here. Now, does this kind of match up before we get too far here? Look, here's my original equation. If you would have balanced this equation here like you would have done in whatever else, O2, I would have put a 2 here. If you would have balanced this and a 2 there. Does that kind of match up with what's down here? Look, 2 magnesiums, O2, O2. 2 Mg2 pluses and 2 O2 minuses. 2 Mg2 pluses, 2 O2 minuses, yes? Okay, so you don't have to balance it initially because it's going to balance it after when you balance out the electrons. That's the purpose of balancing out the electrons. Okay, good so far? Yes? While we're down here, we better talk about, always going to be asked, what is the oxidizing agent? In this case here, I don't want you to tell me, I just want you to look at that. What is the oxidizing agent? Look at those two and tell me which one is the oxidizing agent. And you would tell me it's what? Magnesium, or I guess your other option might be some oxygen. The oxidizing agent is the what? Yes? Why? Because it is being reduced. Yes? The one that's being reduced is the oxidizing agent. Yes? You're going from, look, I even wrote it here, reduced. Which one's being reduced? Oxygen's being reduced. Oxygen's going from a 0 down to a 2 minus. It's going down in charge. It's being reduced. Therefore, by definition, that is your oxidizing agent. Which basically means that this, of course, would be your reducing agent here. Is it? Is magnesium being oxidized? Yes. Magnesium is losing 2 electrons. It's being oxidized, so it's your reducing agent. Make sure you keep those definitions straight, because that's a big deal. Okay? When I say a big deal, I mean a big deal. Big, capital big deal. Okay? Good? Next. Decomposition of zinc sulfide. Do that one. Or at least write out the equation. Alright, so zinc sulfide looks like this, 2 plus 2 minus. Decomposition gives you zinc and sulfur, like so. Decomposition, of course, remember, is this compound breaks into elements, right? If you're going to put, please don't, zinc sulfide, if you put it into water, that's dissociation. Then you might get zinc 2 plus and S2 minus if you put it into water, because water is polar. It pulls that compound apart. That's not what happens when you decompose it. When you decompose zinc sulfide, it breaks up into elements. Okay? So that's kind of what you're looking at here. This would be a 2 plus. This would be a 2 minus. This would be a 0. This would be a 0. Elements have no charge. Right? So, up to you which one you want to start with. I kind of work left to right, but you don't have to. You know, you can write down both of them and then decide which one is which. Zinc 2 plus turns into zinc solid. Okay? And for that matter, if you don't want to even put electrons there yet, you can even go to the next one. S2 minus turns into S8. Okay? If you really want to, kind of thing. Those are the two parts you're dealing with, right? There is only 2, so that's pretty much it. Now, how does zinc 2 plus become zinc solid? What has to happen? Where would I put electrons, left side or right side, to make that work? Zinc 2 plus becomes zinc solid. Where would I put electrons, left side or right side? Left side or right side? Left side or right side? Left side. Okay? So I'm going to add 2 electrons here. Look, 2 plus 2 minus 0. Left side, 0. Yes? If I put the electrons there, is that my reduction or oxidation? Reduction, absolutely. That's my reduction half reaction. Okay? It is gaining electrons. I guess by default, this probably would be my oxidation, I would assume. Has to be, I guess, right? First things first, but this one here, I got 1 S and I got 8 over there. So I want to put 8 there. Okay? Secondly, I want to add some electrons. Well, I already put them on the left side for the first one, so I guess these probably have to go on the right side. It's oxidation, so I'm losing electrons, which means I write them on the right side. I'd add 16 electrons over here. Okay, I'll just finish this one up real quick. Just give me a sec. So 16 minus, right? 16 minus, 16 minus. to balance these two out, if I'm losing 16 electrons, I have to gain 16 electrons. So how would I figure that out? Times 8. Yes? Okay. We'll add these up. And we get 8 Zn2 pluses. And 8 2 minuses. Solid. And that will give me 8 zinc solids and S8 solid. Okay? And that would be your final equation there. Last things last here, of course, don't forget. We will be asking you which one is the oxidizing agent, which one's the reducing agent. That's super duper important. They always happen on the reactant side, of course. But look, this one is being reduced. Zinc 2 plus is being reduced. So it is your oxidizing agent. Okay? And sulfide is being oxidized, so it is your reducing agent. Okay? And they always have to go together like that because, of course, electrons that you lost equals electrons that you gained. Yes? Okay? So that's your OA and your RA. And that's super duper important. Okay? All right.